it, and I'll go full screen. Can you see the full screen mode? Aditya, can you confirm it?
Yeah,
All right.
it's there.
So
Able to see.
as Aditya has already introduced me, I am an assistant professor of aerospace engineering in the University of Birmingham, and I am very much enthusiastic about using open source software. And because my background lies in computational fluid dynamics, I'm very much interested to promote the use of OpenFOAM uh, everywhere around the world. And particularly my interest is in Indian researchers because I belong there. I have done my PhD in IIT Madras, and I know the pain of learning this kind of codes without much help. So I hope that today's session will give you the head start to go and start with your first simulation in OpenFOAM. So let's go ahead. And this is a disclaimer that we always put, that it is not offered with any official OpenFOAM producers or distributors. All right. So I have recently joined the aerospace engineering department of University of Birmingham, where I'm trying to establish my own research group in bio-inspired fluid structure interaction. And just to give you a brief background about my research, I do try to understand how the small flyers exploit the aerodynamic and fluid structure interaction mechanism to make their flight so elegant. And we try to understand their flight mechanisms and implement those knowledge in building, futuristic air vehicles. All right, with that, let's go ahead and get started with OpenFOAM. I belong to the documentation and tutorial technical committee, where all together with the effort of many researchers around the world, we try to document the source code, document the tutorials, and I will show you in a bit some of the links which are very useful in that regard. So apart from that, you know that there is an effort also from the OpenFOAM governance that to produce an OpenFOAM journal, which is a dedicated journal where basically the developments of OpenFOAM are published. And it is very unique in a way that once one paper gets published, you get a chance to communicate with the paper to use their source code and develop on that. So for that, there is a forum created in the journal website. So if somebody is doing some development in OpenFOAM or interested in future, they might want to publish in this journal. And I'm very proud to present here that the first OpenFOAM journal issue cover featured one of my PhD research as the cover photo. And the second one was also one of my postdoc results, which was chosen as the cover pick of the OpenFOAM journal. All right. Now, I do not have a complete understanding of the all audience, what is their background is, and whether they know what is OpenFOAM or not. So I will, as mentioned, imagine that most of you are beginners. So please excuse me if some things are very basic for you, but I will start with a very basic uh, definition or explanation what OpenFOAM is and what are the definition of different classes and objects of OpenFOAM, so that if somebody is just for the first time hearing about it, can also get some idea to get started. So the full form of OpenFOAM is that open stands for open source code. So the difference between the open source code and the commercial or in-house code is that open source codes are freely available and they are distributed throughout, where actually people can download the source code and look into it, what is written, and can understand it, build their own code, manipulate it, and recompile it to build their own solver. And that is where we would aim towards the end of this session, to show you some of the source codes that actually comprises the variety of fluid dynamic solvers that OpenFOAM contains. All right. Now, FOAM is an abbreviation, and the full form of it, as given here, field of operation and manipulation. Now, it is nothing but a set of open source libraries for continuum mechanics. So why I name it continuum mechanics because it is not only for fluids, it also has solid mechanics solvers where you can solve solid mechanics problems. And as a whole, you can also solve fluid structure interaction, and you can also solve different type of multi-physics problems apart from fluid and structure, such as electromagnetism and anything which is governed by a partial differential equation, because OpenFOAM gives you a capability to code a partial differential equation yourself within the solver and modify it. All right. Now, of course, the first thing that you need to know about it, that what is the programming language that it is written in, and that is C++. And as part the basic structure of C++ programming, it follows an object-oriented programming. And of course, the CFD methodology comes the next. So what CFD approach or CFD methodology has been implemented in the solvers of OpenFOAM, that is finite volume method, as opposed to finite element solvers, which are available commercially, like COMSOL is written in finite element solver, etc. All right. Now, next question that motivate us to sit in this session together is that why should we learn about OpenFOAM? And I tried to jot down some of the points. First thing is that it is open source. It has a large community based and it is free. So if you are in industry, we have some of the project, particularly I would like to mention the project FOSSI, which is run in IIT Bombay, and I'm quite involved in it, has an ambition that even we translate the use of these open source softwares, including OpenFOAM, to the Indian industries, so that you don't have to purchase the licenses for commercial softwares like ANSYS Fluent and COMSOL, like by lakhs of rupees. Okay. Second is that an efficient libraries of C++ modules, and it contains a high-level programming. And I will come to explaining in a bit what do we mean by high-level programming. It means that you do not have to write in a machine-level language, and it is the code in OpenFOAM is actually consisting of a lot of different functions and libraries which are already defined from the base level. So you can directly use them and actually do your solver development without just defining every function of them yourself. It is more or like if you are used to MATLAB. So MATLAB is also a kind of an high-level programming where you don't need to code for every function, but you can use some of those functions directly. Okay. And FVM solvers can be tailored for a specific need. As I said, you can see what is written. So without just, closing your eyes and clicking something in a commercial software, you can go through the source code, read what is written, change whatever is needed, and then recompile the code as per your need. All right. So it has extensive multi-physics capabilities, and it has cross-platform coupling, such as one of the example is fluid structure interaction, where you need a fluid solver, you need a structural solver. Now it is up to you whether you choose the structural solver from OpenFOAM or you use some other open source softwares which is written in some other methodology, such as finite element analysis for structures. For example, if you have heard of codes like Calculix, Deal2, these are the finite element based structural solver which are available in open source. We can actually couple our fluid solver, which is nothing but an Navier-Stokes solver, with a third-party structural solver using another separate external coupling platform such as Precise. Okay. Now, a disclaimer before going actually into the OpenFOAM and coding into it, it's that it's no black magic. Okay. So this is my personal view, is that you cannot do things in OpenFOAM very much blindly. You cannot assume anything and just click it. So don't expect to click it and getting results. If you expect that, you should better be in the commercial softwares. All right. Now, there is not a single executable, Okay, so every problem, every physical problem has a different governing equation. And then if your problem demands a different governing equation to be solved to understand the physics of the problem, you need to code that partial differential equation or the governing equation down into a new solver. For that regard, the understanding of the source code is a must. The another main drawback of OpenFOAM is that there is no native GUI. So it is not yet developed properly. There are some efforts going on, I know, within or outside India, but it has not been officially published. So there is no officially available graphical user interface for using OpenFOAM. So for that regard, we need to use it in mostly in terminal, and which we call as command line interface. And we will try to see how to do that in a while. And I have to accept that it is not the best documented code library that we can expect. So it needs a lot of improvement. But I have to say that when I started using OpenFOAM back in 2014 to the journey of 2023, it has been improved in leaps and bounds. But still, there is some improvement which is continuously being done from the different technical committees, and I hope in future it will improve very fast. Okay. All right. So some of you have raised your hand. I don't know whether I can allow you to speak. So, okay. So I see someone raising your hand, and I don't know whether I can unmute you.
Yeah, Vignesh, we can unmute 2 to 3 participants and we can take up the questions.
Hello.
Yeah.
Yes,
Yeah,
please.
myself, Jose Prashop. So my question is that these sessions are recorded and will be shared to the participant later, because I have some inconvenience for the time being to attend to this.
No,
But
these
I
are
wish
not.
to.
We have already put in the mail itself or inform in the mail that sessions recordings will not share. PPT we will share. All the documents we'll share it with you. Yeah.
I will share all the tutorial files also, but about the recording, I leave it on the policy of NPTEL.
Yeah. One more thing I want to focus. If you have any technical doubts or you want to discuss something, then you can just raise your hand. We can address the questions. Otherwise,
Yes.
you put in the chat box and we will see, and we'll reply you at the last. If some operation issues or if you have some queries, then
Yes.
these things we can reply it in the chat
That
box.
is also my request. Otherwise, we
Yeah.
won't have enough time to discuss all the technical stuff.
Yeah.
All right. Okay, let's
So
continue.
Chandan, what I can suggest, we can not take a questions via raising hand. We can just check the chat box and we can reply for the particular questions.
All right. Okay.
Yeah.
Whatever you feel comfortable. So, okay, let's go ahead. So let me give you a very brief 30-second introduction on the history of OpenFOAM. And you must know the name of these two scientists, Henry Weller and Professor Henry Weller and Professor Herb Chesak. They are the main contributors of the base code of OpenFOAM, and it was actually developed as the title of FOAM, FOAM, Field of Operation and Manipulation at Imperial College London. And then slowly, as time has gone, it has gone through different stages of transformation from open source, and then at some point it was supposed to be commercialized, and so on and so forth. But just to get that the effort has been started in 80s in Imperial College London. All right. Now, this is where we basically start with our practical understanding on how to use OpenFOAM particularly for CFD. So you have to know that the main code repository of OpenFOAM has 3 different forks, and which is very, very interesting and as well as very important to understand, because often people get confused which versions to use and which version would be useful for my particular project. And I get numerous questions about it. So I thought, let's start with that fact. So the first fork of OpenFOAM, which is available through www.openfoam.org. They are actually maintained by OpenFOAM Foundation. All right. And they are supposed to be called as official standard release, and the releases happens every 1 year. All right. And the current version is version 11, which has been released this year. So every year they starts from like 8, 9, 10, 11, something like that. All right. So the next fork is available from www.openfoam.com. And this is maintained by ESI OpenCFD. And I am very much involved with this group of people, this community of people. So each of these releases have different community of people, and they also have a lot of overlap, but I mostly engage with the community of OpenCFD. And it actually releases two versions every year, and one in June and one in December. Now the nomenclature of these versions are normally you would be able to see that OpenFOAM version 2306 means this version has been released in 2023, and in June, that's why it is 06. So soon in December, the next version will come up as OpenFOAM version 2312. All right. And the last fork is called Foam Extend, and which is also useful in many projects because some of the capabilities are explicitly available in Foam Extend, which is not available in the other forks. However, this is a community-driven development branch, and the current version is Foam Extend 5, and there is no regular release of the next version. So it happens in 1 year or in a couple of years. But however, you might be interested to explore this repository because there are some of the interesting features such as from CFD perspective, immerse boundary method, all those capabilities which were first included in Foam Extend, and now slowly it's getting ported into the OpenCFD version. All right. Now, going ahead, the first thing I think that I just wanted to start with giving you a visual idea of what we are going to look at normally. So when you set up a CFD case, or we call it as a tutorial case or your project case, of course, it has different components, which we will discuss, but it is just to start. I wanted to start with a pictorial view so that you remember these names at least when I show you actually for a tutorial case. So any OpenFOAM tutorial case will actually have three main folders. One is 0, another is constant, another is system. All right. And I will describe each of these folders in greater details in a while. But just for now, keep it in your mind that you would be looking into these folders again and again. So any CFD case folder will have 0, constant, and system folder, and the constant folder will contain the mesh files. The name of the mesh file is polymesh folder, within which you will have all the mesh informations and other properties that we will discuss in a moment. So the main motive of showing this now is that please keep it in your mind that whenever you look at any case folder in OpenFOAM, you would actually look into 0, constant, and system folder. All right. So that is where this comes. Now, as I told that the constant folder will have polymesh folder, which will have the mesh information and other properties. Now the system folder will have control dict, FV scheme, FV solution, and the 0 folder will have the initial and boundary condition in terms of your state variables. In this case, I'm showing two state variables. One is pressure, another is velocity. All right. That's it. So now going further, let me look into sorry, how can I look into the chat? All right, I cannot in the full screen. So
Are you able to see the chat?
Yeah. I'm just
Yeah.
going. Okay. Interested. All right. So nothing much technical about what I am telling now. Okay, that's fine.
One
So I,
question I think is there, Chandan. He asked like about finite volume methods for solid mechanics and multiphysics as well.
yes. So what is the question? I can't find it. So can you read out the
So question from Anupam. He asked, does OpenFOAM use finite volume methods for solid mechanics and multiphysics as well?
Yes, that's a very good question. Yeah. So the quick answer is yes. Any code in OpenFOAM is actually written in finite volume method. So even for solid mechanics, the codes are written in the discretization formulation is in finite volume method. And they are quite well validated and they are almost equivalently accurate with finite element schemes. That is the answer. So Aditya, can I request you that to you and interrupt me if you see any interesting question? Otherwise, I will
Yeah,
just
yes.
time looking at
Yeah,
it.
yeah. So one more question is that is like most of the people are misunderstood on that. So what is the difference between OpenFOAM and ANSYS?
All right. So any CFD, which is computational fluid dynamics software. However, I don't classify OpenFOAM as a software as a whole. It's a bunch of C++ codes. And any software is a bunch of codes, but why we call them as softwares is that they are either commercialized and available as a package, they cannot be modified, and so on and so forth. So basically, quickly to answer the question, what is the difference between OpenFOAM and ANSYS Fluent, particularly, which is the computational fluid dynamics part, is that any CFD software can be classified majorly, in my opinion, in three different ways. One is the commercialized version of the code, or which is licensed, which you cannot use without subscribing to it or without buying appropriate licenses. ANSYS Fluent is one of them. And the second category is the open source software, which is distributed freely, and the developer or who has written the code actually strongly encourages others to use it, modify it, and develop it based on that. And OpenFOAM, as from the name it is clear, it is an open source library of CFD codes, which is freely available and can be modified, and so on and so forth. The third category is also available in the form of in-house code. So if you, for example, go back to US national labs, you would say that every very established labs, like some labs in NASA and so on, they have some sort of legacy codes, which is written in like 50 years back, 60 years back, and they still use it because it is still way more accurate or can be very appropriate for the kind of problem they are tackling, and so on and so forth. And with that, every research group in India or outside globally might have their own developed CFD codes, which is written by their group and improved for years within their group, and they use it for their own research investigations. They are called in-house codes. So I think it is now clear.
Yeah.
Now, going back, I mentioned at some point that OpenFOAM uses high-level programming, right? So what do we mean by high-level programming? There is so I will just give you a overview example here, is that in the left, you see a partial differential equation based on a scalar phi. You can say which is nothing but a generic form of Navier-Stokes equation, which has the unsteady term, convective term, diffusion term, and the pressure gradient. And these partial differential equations actually govern different physical systems. Particularly for fluid, we use Navier-Stokes equation, and more particularly, we can consider incompressible fluid mechanics problems, which I will be discussing here. So considering that fact that the governing equation is incompressible Navier-Stokes equation, all right? Now, if you want to write it or code it in OpenFOAM, you really don't need to define how to discretize a time derivative. So if you have any experience with CFD codes, or if you have simulated by writing your own code, you know that, but to define a time derivative, we either have to write or discretize the time derivative term in a backward difference or a forward difference or a central difference formulation, and so on and so forth. So each of these terms of this governing equation can be discretized in different way, all right, in different CFD approaches and different discretization mechanism. Now, to write this equation in OpenFOAM, you basically don't need to actually do any sort of those things. I'm just searching for a highlighter maybe, or sorry, laser pointer. Yep. So basically, you can see that the first term, which is a time derivative term, the unsteady term, is actually defined with a function just name as ddt, which is very easy to understand. All right. Now, this is implicit because the rho is not outside the derivative term. So that's why we have ddt function of rho comma u. And I will come back to the explanation of what is FVM and what is FVC. So for now, just know the name of it is as finite volume method and finite volume calculus. And so the point is that if you want to, for example, define this divergence, right? So this delta operator is nothing but it's a vector operator which works on a vector and defines its divergence or curl, etc. So for this divergence term, we just use a function called div. And then for Laplacian, because here there is like dot of two delta operators, we use a function called Laplacian. For gradient, we use a function called grad. So it is more or like a high-level language like what we use in MATLAB, that we do not separately define it. That doesn't mean that this is not coded. This is already coded. You can also go to the source code of these functions, which is already written within the libraries of OpenFOAM, all right? So that now as a user, you do not need to write a code separately for Laplacian. You can just use the function of your Laplacian, which is already available in OpenFOAM. And that is the reason we tell that OpenFOAM coding is a bit of high-level programming, which is easier, all right? Now, coming to the fact that very quickly, these are the pros and cons. And somebody was asking what's the difference between the commercial softwares and OpenFOAM. The main difference, I would say, that the source code, which is not available for commercial codes, but it is available for OpenFOAM. And of course, that leads to the economic perspective of it, that if as an industry or as a startup, if you open a CFD startup and you do not have much investments and you are just trying to establish your business, you do not have money to buy the commercial licenses for these established softwares, but you can easily learn open source softwares and open source alternatives of it and use it cost effectively. All right. All right. Now, coming to what is the basic stepping stone of computational fluid dynamics. Now, again, I'm assuming that most of you all are very much beginner in the undergrad level or master's level, starting with CFD. So I know that there are quite a few faculty members who might be very expert of this field. So excuse me for repeating these things, because this is the motive of this session, that telling everything from very basic. So the basic stepping stone of any computational fluid dynamics simulation is basically, I categorize it in a three-way system. One is pre-processing, all right? In the pre-processing step, what we do is we first define a sketch of our problem definition, like what do we want to simulate, whether it is two-dimensional or we need to do a three-dimensional simulation to capture all the physics or not, etc. Then when we make up our mind on the type of simulation we need and what type of problem definition that we need to come up with, we try to replicate that in the form of a geometry of the body. For example, you want to understand what happens in the leading edge fluid mechanics of a swept wing, which is completely three-dimensional a body, right? So for that, we need to first make a geometry of the profile of the swept wing that we need to incorporate into our CFD system to understand what happens to the flow past that body. All right. Now, once the geometry is done, we try to come up, and of course, not only the geometry of the body, associated with that, we have the geometry of the domain. Now, we have to decide how big the domain of our computation will be, and whether it enables the redundancy of the boundary conditions. That means that if our domain is very small, there will be a lot of effect of boundary condition and our solutions will not be domain independent. So by our experience from the literature, we can first come up with our preliminary reference domain and make the geometry of it with the geometry of the body. Then we basically try to mesh it. Now, the meshing can be in many different ways. And I normally think the meshing in a way that it's an art, all right? So any user or any CFD engineer, they will mesh their system in a very different way. So it cannot be the same for everybody. Now, there are some basic guidance on that, whether to use a structured mesh, whether to use unstructured meshing, whether to use hybrid meshing, involving both structured and unstructured meshing. That all depends on the nature of the problem, on the computational resources available, and the expertise of the CFD engineer. All right. Now, when we have geometry and mesh ready, that completes the steps of pre-processing. However, there is a small part still is left, is that setting up the simulation. All right. That means because we are trying to solve a partial differential equation, we need initial condition as well as boundary conditions. Now, before we go to the next step, we need to set up the initial and boundary conditions into our case setup. All right. And also, we need to basically set up all the CFD control parameters which will control the solution. So the next step after pre-processing is solution. Now, to solve this partial differential equation, we need solvers, which is basically Navier-Stokes solver in our case. And we solve the partial differential equation by discretizing the equation in the grid points in a CFD approach that we think it is appropriate. And as a result of this solution, we get the state variables or the field variables such as pressure, velocity, etc., which are dependent variable of this partial differential equation. And we get it at every point of our mesh, in every coordinate of our mesh, with every time step. And so time and the coordinates are independent variables of the partial differential equation. Now, at this solution stage, either we can do the whole calculation serially with only one processor, or we can parallelize it by involving multiple processor and nodes if we use it in a cluster or high performance system. All right, high performance computing system. Now, once we have the solution, which are the field variables in terms of mainly pressure and velocity or temperature, if that is a dependent variable of your governing equation, we do post-processing. That means we use some analysis techniques to derive other quantities from that basic field variable, such as we compute vorticity. I will show you how to do it from the velocity field, and etc., etc. And then we try to interpret the physics. All right. So these are the very basic three-way component of any CFD simulation, in my opinion. Now, next it is coming is that what do we use then? So interesting part is that for the solution, we use OpenFOAM solvers, but it is not necessarily important that for the pre-processing and the post-processing, we have to use OpenFOAM. So OpenFOAM is quite flexible to allow us to make our geometry and mesh in ANSYS if we want to. In any other third-party commercial softwares, if you think that they are more proficient in making your mesh appropriately, which is the case for complicated geometries. All right. However, we have open source alternatives for it, and I would highlight two of them, which is very, very nice and useful. I want you to learn about it. One is GMSH, another is Salome. So these two open source meshing and geometry softwares are immensely useful if you don't have access to any commercial meshing or geometry making software. All right. Now, the solver in OpenFOAM are categorized in different way, depending on their applications, such as incompressible, compressible, multi-phase, etc., etc. And then post-processing also is equally possible in both commercial as well as open source component. The most popular open source option for doing the post-processing with OpenFOAM data is ParaView. Again, it is immensely powerful and you can actually do many things with it. Second one is Visit, which is also immensely powerful. And of course, you can go to the commercial stage of it and do it in TechPlot, which I think is very popular among CFD engineers. Right. So now let us get started and let's come to some of these things and see this actually in your installed OpenFOAM folder and get to know the paths of the source code, right? So for that, I would stop sharing this screen and I will show all of this actually in my terminal hands-on so that you know what to do, all right? So at this stage, I ask Aditya if there is any interesting question that I should address to.
Not, I think in chat box, people are interactive, so most of the questions are addressed by the participant as well. I didn't find any question how much programming knowledge we need.
All right. Okay.
In OpenFOAM, is OpenFOAM used in helicopter aerodynamics where the rotor blades are moving? Yeah, you can use it, I think.
Yes. So about the application of the problem, as I already mentioned, that I'm not going into these specific applications because everybody's project is different. I would just get you started with OpenFOAM within the scope of this session, and then you can go ahead with it and apply it in different fields that you want. All right. So if any of you have OpenFOAM installed with you and you are with your computer or laptop, please feel free to do it with me. And if you have any doubts, you can ask me. Okay. So before going into OpenFOAM directory and showing you stuff, I want to show you some basic things about this terminal, right? So the window that you can see now is called terminal, or in more technical term, it is named as command line interface or CLI, okay? And I think it's very basic. And if you don't know, it is very useful to learn this before learning OpenFOAM, okay? Because OpenFOAM is inherently very much native to Linux platforms or Unix platforms such as Mac, Unix, and Ubuntu in Linux. However, you can also use it in Windows, but for that, you need to use the inherent Linux component of the Windows, which is called Windows subsystem for Linux. Now, yesterday I have shared one document which actually shows you the installation links and the steps for that. And of course, if you are very new to it, you might get some problems with it, which you can resolve with someone, or I hope that the steps are very clear. So you will be able to install OpenFOAM in whichever operating system you want, particularly in 3 different operating systems, Windows or Mac or in Linux. In Linux, it is very easy. In Mac also, it is very easy because for installing into Mac, we use something called Docker. which is nothing but a container and where we put the OpenFOAM installed version and use it in our terminal using the Unix operating system of Mac. However, in Windows, it's a bit tricky, but it is not difficult. The stepwise installation steps are shared within the link. I've also tried to share one of my old installation video that I have previously compiled. I think it still holds for Windows 10. A bit of change might have to be done for Windows 11 if you have something. All right. Now, assuming the fact that you can successfully install OpenFOAM in your computer, you basically have to now know a bit of basic comments about the terminal or how to operate your computer through this command line interface. All right. So, right. So basically, let's starting with that. So I am in a current place in the terminal, and the first thing that we actually want to know that where am I situated or where am I located, right? So for that, the Linux or Ubuntu command that we use, we use is called pwd, which basically shows you the path where I am in. And you can see that the path clearly shows that I have a main root folder home in my computer. Then I have ADF, BOSC, desktop, and cylinder 2D. I am within some folder. All right. Now this allows you to see the path. And then once you see the path, you actually go to other folders. Yes, the question asked, is it a Ubuntu prompt? Yes, it's a Ubuntu terminal, but it's the same as the command prompt in your Windows. Or if you have already installed Windows Subsystem Linux, you can directly open WSL and can use it. Okay. Now I am showing this exercise or all these tutorials in an inherent Ubuntu system where I have already installed OpenFOAM version 2306, and which is the latest version of OpenFOAM in the fork of openfoam.com. All right. Now, I'm going a bit fast because we are almost past going to be 1 hour. So I have to gear up now. So now basically, I want to go to my home folder. All right. If I want to go to my home folder or any other folder, the command is cd. Okay. The command is cd to go to any directory. And if I want to go to my home directory, I would just type cd $home and I will go somewhere. All right. And let's see where I am in. I am actually in my home ADF BOSC. All right. Now, some people are asking why it is showing OpenFOAM 2306. I will come to that fact in a while. But irrespective of that, what I'm showing is actually can be done in any case. Okay. So you can see that my home directory path is /home/ADF/BOSC. Now, once your OpenFOAM is installed, okay, to activate the terminal for OpenFOAM environment, you have to actually activate the basrc. There is a basrc file located, which I will go to now, of OpenFOAM. And you can do that in two different ways. The first way is to set up an alias for activating the basrc file, which I have already done, and which is nothing but OpenFOAM 2306. So this is a keyword, okay, which I have already set up as alias to source the basrc file, but I will anyway show you what to do to source it otherwise. All right. So now if I enter command, it activates the terminal for using OpenFOAM, and it shows me that, see, I have OpenFOAM version 2306 installed. This is the build, Arch platform, etc., etc. All right. Okay. Now, what is alias? It is basically, you can Google it up. I mean, if I try to explain what is alias, I will take 15 minutes, which the workshop doesn't allow me to do because I want to cover something on OpenFOAM. But please Google it up. You will get to know. Alias is nothing but setting up keywords to execute some big command or big path, which has to be set up in your system basrc file. So basrc is a file which is located in your system when you turn on the system or activate any terminal, that actually automatically applies all those settings. All right. Now, basically, once we activated the OpenFOAM, the first step is to go to the installation directory. So I want to see where my source codes are located and how does they look and so on and so forth, right? So to do that, the command that we want to use is called FOAM, FOAM. It's also a namespace in the C++ code for OpenFOAM. So in the standard C++ code, when you start writing it, you have to start with a namespace called std, right? Now, in case of OpenFOAM, the namespace is FOAM, foam. And by entering that, we actually go to our installation directory of OpenFOAM. Now, keep in mind that to be able to use this command FOAM or whatever I will show you now, you have to first activate the OpenFOAM. And to do that, either you have to source the basrc, and I will show you how to do it. But if you have already set up alias to do that, you can just type the keyword name and it will activate the OpenFOAM. Now, the important thing is that you can see that my installation directory of the OpenFOAM is /user/lib OpenFOAM 2006. So all my source code or installation file and everything is located within this folder. Now, this path can be different for you. It can be wherever you have installed your OpenFOAM. Okay. It also may depend on the operating system. So if you see this path in Windows, it may look a bit different. In Mac, it may look a bit different because it will be in the Docker. In Ubuntu, it shows more straightforwardly the actual path of OpenFOAM installation, right? Now, next thing is, if we want to see what is there within this folder, so for that, we have to use ls. So ls, again, a command line interface command. And if we enter, we actually see all the folders that are actually available within this folder, right? Now, I will now explain some of the folder names which are important in terms of OpenFOAM uses and knowing the source code. So first, the allwmake is nothing but it's a script file which you would have used to install OpenFOAM. That means this is a script file which allows you to compile the source codes of OpenFOAM and make the executables. All right. Now, the next folder, I think, is an important folder, is called applications. So remember this folder name because within this folder, we have all the solvers located or situated. All right. So to go into this folder again, I use the same command cd. And if I go to cd applications, I go into this folder and then I see what are the contents of these folders. And you can see there is a folder called solvers. All right. And within that solvers, all the solvers are located. So let's go into this folder, solvers. And if I see, sorry, I did something wrong. Okay, I did capital LS, that is wrong. So we have to give small ls, that's a typo. So if we do ls within that solver folder, we can now see all the solvers are actually categorized into different applications: combustion, acoustic, incompressible. And this incompressible is our today's interest. And we will mostly go into this folder and see some of the tutorials and describe the files of it. All right. So what is the question? Okay, I think most of the questions are related to installation. Now, as I said that within these 2 and 2.5 hours, I cannot show you how to install it. Then I cannot show you how to do simulations. All right. So you have to do it yourself and try it. And I have shared the links, which should be pretty much straightforward to follow the steps and do as per the operating system that you want to install in. Right. So now that you know, so this is a big thing. You know actually where the solvers are located in your OpenFOAM installation directory, which is within the main directory, you have applications and then solvers. So now the next comment of Linux that you would need to go back in the directory is actually to go backward. And if I want to go backward, we do cd ... and now you can see I have come out of solvers and now I'm in applications. I do again cd ... I am in the main folder, which is OpenFOAM 2306. And if I do ls, I come back to the main set of folders. Now I know which is application. Bin folder is where my executables are located. That's fine. Now this folder is important, which is etc. And if we go to etc, I will only mark one important file, which is this file, which is basrc. Can you see this? So within the etc, we have a file basrc, which you need to activate. So by typing the command OpenFOAM 2306, we actually, what we did is we did source, right? And the path where it is located, which is for me home, ADF, BOSC, I think, no, sorry. The path of OpenFOAM is different. It's user, leave, OpenFOAM, and OpenFOAM, etc. And then we have basrc. So this is the comment that you need to make alias of to source this basrc, to activate OpenFOAM, okay? Right, so I see that some of the comments says OpenFOAM is not installed, some of the files is not there. So I suggest you to follow this up and at least note it down for yourself, what I am doing. Once your OpenFOAM is properly installed, you will be able to follow it. So it is global for any kind of installation. It is irrespective of operating system, what I am showing, okay? Only the paths will differ. Right, so is it clear? Now, the other folder which is important here is the SRC, which means, can you see my cursor? So SRC folder, this is the source code folder. And the other important folder is the tutorial folder, which we'll basically copy and discuss and simulate and try to discuss what are the tutorial files and how to do the simulations. All right, now let me clear the screen and start from the beginning. All right. So Aditya, do you have anything urgent to answer at this stage? I cannot read all the comments.
So one question actually it's repeating is OpenFOAM is Python friendly. So I observed this question previously also.
What is the question?
Is OpenFOAM Python friendly?
This question actually has no meaning at all because OpenFOAM is Ubuntu friendly. I mean, I think someone wanted to ask which operating system is easier for using OpenFOAM. I think that I have already mentioned that Ubuntu is, or any Linux platform is more easier to use OpenFOAM. So if we use Windows, you actually have to install Windows subsystem for Linux or any virtual box and install Ubuntu in that. Whether it is Python friendly or not, what I don't understand the actual meaning of it, because OpenFOAM is written in C++. So it is not written in Python. Okay. So I do not understand what do you mean by Python friendly. Of course, you can cross-couple OpenFOAM code with some Python code. As I said, that OpenFOAM can be cross-coupled with different other codes. All right. Now, I would suggest you to actually, it is in the PowerPoint presentation, but to note down these comments. So I want to show you the tutorials first, because now we have passed 1 hour. And now I would try to start discussing on the case file of an OpenFOAM, what they mean, and how do we set up the simulation. And we will try to do one simulation from the explaining from meshing to visualization. Then I will come back if there is any time left. I will come back to a bit of source code again and explain how to modify it. All right. So I think if I go farther into the source code at this stage, you might not follow, as many of you, I understand, has not yet installed OpenFOAM, right? So let's make our life easier and copy one tutorial folder to our desired folder to do all the steps, pre-processing, solution, and post-processing, and understand how OpenFOAM does it. For that, the folder that we need to go on is tutorial folder that I just showed is located in the main installation directory. And once I have activated the OpenFOAM installation, OpenFOAM environment, we can use this shortcut command called TUT. Okay. And you can see that by typing just TUT, I have gone to that path automatically, which is nothing but my OpenFOAM installation directory, which I got by typing the command foam, FOAM. And within that, there is a folder called tutorials. All right. Now, if I want to see the content of it, I put ls again, which is a command line interface, very basic command. We see that it is categorized. The tutorials are also categorized into different application. And I am mostly interested in incompressible. All right. And when I go to incompressible folder, I see that within the incompressible, I have different folder in the name of the solver. Okay. Now, these solver names are named actually. Okay, I will show you where the alias for TUT is written. That is, it is already written within the OpenFOAM file. If you are interested, I will show you that. But I just want you to first show you one tutorial first so that you can bit of follow how to do the simulation in OpenFOAM. Right. So what's this question? Have you tried creating this folder through AI? This discussion is not on artificial intelligence. This is on OpenFOAM. All right. So basically,
And then maybe you can continue. We can take the questions later.
no, it's automatically popping. That's why. Right.
Okay. So what I will do, I'll just stop the messages for a time being. You explain the concept, and after then I can just enable it now.
No, let it be. Let's see. Let them type whatever. So basically within that, we have to choose a solver first, right? Now, we need to decide in which algorithm we need to discretize our Navier-Stokes equation. And particularly for incompressible Navier-Stokes equation, I will first choose the most basic solver, which is IcoFOAM. All right. So IcoFOAM is the very basic incompressible Navier-Stokes solver, and I will show you the source code of it, what is written here. And you will be relating it to what I have shown as high-level programming. So now, before that, let's go to IcoFOAM. And within that, if I will see there are multiple tutorials already available, and we will first copy the most basic tutorial, which is lead-driven cavity, where we have a cavity, rectangular cavity with steel fluid, and we have a lead, and the lead has a velocity, finite velocity. And if we move the lead, we will try to see what happens inside the fluid volume. All right. What type of changes it happens in terms of its pressure and velocity, so on and so forth. So to do that, we go to cavity, and within the cavity, there are multiple modifications of the cavity. So this is a way you go to the tutorial. You go one step, what type of problem you want to solve incompressible. Within that, you next choose which solver you want to use for your problem. Then within that, you have multiple tutorials which shows you the use of those solvers. And you choose one of these tutorial file, and before modifying it, please copy it to your desired location. Mostly, I prefer it to be copied to the user directory, but let's, for easier things, I will copy it to my desktop, for example, right? So to copy a folder in Linux, we use the command cp, and to copy a directory, we use cp-r and all the files cp-rf, and I copy cavity, this folder, to my desktop. And I know the path of my desktop, and your path will be different. And if you know your path of the desktop, I just enter, and it has gone to my desktop. And let us see what is there in my desktop. And you see that this folder I just copied from the tutorial to my desktop, right? Okay, so you cannot see my, you can only see my terminal. So stop sharing. Okay, how to start sharing now? Share screen, and where is my folder? Okay, I'm searching for the folder. Let me check. Matt. Okay. Just give me 2 seconds. I'm trying to share my folder. So for some reason, my folder is not coming. Okay, let me try to show you in terminal itself. Okay, so let's go to my desktop by doing the cd command, and I know the path of my desktop. Okay, so I will go to cd to this path, and now I am in desktop. Let's clear the screen. And if I see in my desktop, I will see already there is this cavity folder, which I have already copied from the tutorial. All right. So now, going back to what I showed in my presentation, which I told you to keep in mind, that this is a tutorial case or any CFD case that we need to simulate, which will contain how many folders? Primarily 3 folders. One is 0, one is constant, and one is system. All right. Now let us try to see what they contain and what they mean actually, and why do we need them. So if I go to cavity, all right, and let us see within that what is there. And you can clearly see that we have 0, constant, and system. Now, the 0 folder, which I have not told you yet, why it is named as 0 and why do we need it? So 0 folder is the folder which contains the initial and boundary conditions for solving the governing equation, which is the incompressible Navier-Stokes equation in this case. All right. And so it contains all the initial and boundary condition. Okay. So if I go to the 0 folder, I see that I have 2 files. One is pressure P and one is velocity U. Now, which means that I have 2 major state variables, pressure and velocity. And we will go into these files to see what are the initial condition and boundary condition that we have set. Okay. So that is our first step. And this contains in the 0 folder. And to open the file in the terminal, we use an editor called Nano, and which shows you the file. All right. So I hope everybody can see this file one by one. Now, somebody actually might wonder why the dimension of pressure is like that. So every variable in OpenFOAM is a dimensioned variable. So they have proper fundamental dimension. Now, the pressure in OpenFOAM is actually pressure divided by rho. Particularly for incompressible solvers, the pressure P variable in OpenFOAM is defined as P by rho. That's why the dimension is L square T to the power minus 2. Okay. If you can calculate the dimension of P by rho, it will come like that. Now, this is the value. This is the value of the internal field, which means that I will show you now quickly what is our domain. But in our domain, we have some boundaries where we apply boundary condition. They are called boundary field. And we have some cells inside the boundary, which is discretized. They are called internal field. So it is showing that the internal field is set to a zero pressure at t equal to 0. Okay. So that is a one internal field condition. Now the boundary field condition has three different patches, which I will quickly show you what are they. But for now, you just know that there are three boundary patches where we need to give the boundary condition for pressure and velocity. One is moving wall, which is nothing but it's a name that we have given for the moving lead of the problem. And we have given a zero gradient pressure in there. We have fixed walls. Rest of the walls in the 2D problem, in the rest three patches of the cavity is fixed walls. And we have also given a zero gradient pressure. And the front and back, because this is a two-dimensional problem, we are restricting the solution to propagate in the third direction by giving an empty boundary condition in front and back. All right. If it is 3D, then instead of the empty, we have to give an appropriate boundary condition in the third direction also. All right. Now, if I see velocity in the similar way, we see that it has a proper dimension of L t to the power -1, which is a velocity dimension. And again, in the internal field, we set as zero velocity at t equal to 0. And the boundary field, we have the same three patches. Only in the moving wall, we set a fixed value, which gives a finite value of the velocity at the moving wall, which is the top lead, as 1 meter per second along the x direction. That's why it is 1, 0, 0. So y and z components are 0, 0. And the fixed walls, the rest three walls, which is fixed, we give a no slip boundary condition, which actually enables the no normal boundary condition within the wall. And the front and back, again, similarly, because it's a two-dimensional problem, we give an empty boundary condition in the front and back. All right. So now we know what is the boundary and the initial condition for this problem. The next folder, as I said, apart from 0, is constant. So let's go into that and see what is there inside that. Okay. And we see that there is only one file, transport properties, which we will come. But first, let us know why it is named as constant. This folder is named as constant because whatever values that we define within this folder will remain constant throughout the simulation. They do not change. All right. So for example, you want to define the viscosity of the fluid, which does not, if it does not change throughout the simulation, we actually define the viscosity within the transport properties. Suppose you want to define, some other properties which remains constant, such as density, which remains, if you imagine it to be, it remains constant for incompressible flow, we define it there. Now, one folder within this constant folder is missing, which I already showed you before, which is the mesh file. Now, in the pre-processing part, now we have to first create the geometry in the mesh. And in this example, we will create it by block mesh dict command or the block mesh dict tool. And another example I will show you where we use the other meshing tool is called snappy hex mesh. So for example, in this case, we use the block mesh dict command to generate the mesh. We have not done that. That is why the polymesh folder, which contains the mesh information within the constant folder, is missing. So that is something to note. Okay. Now let us see what is there in the transport properties file. All right. So in the transport property file, in this problem, we have only one constant that is mentioned, which is nu, which is nothing but kinematic viscosity. I mean, the names are also very much conventionally with the textbooks that we have learned in the courses. Nu, we know it is the kinematic viscosity, which is nothing but dynamic viscosity divided by the density of the fluid. And we set the nu here, and this new value governs the Reynolds number, right? So for this problem, if we do a dimensional analysis, we will find that the most important non-dimensional group that affects the physics of the problem is Reynolds number. And to set the value of the Reynolds number, we can modify this value of nu. That is one option, how you can modify Reynolds number. All right. So now we know that, and we know that we have not created the geometry and mesh yet, and we only have the transport properties files inside the constant folder. And the next folder is basically is the system. And let's see what is there. Okay. So within system, we see multiple files, and we will now go one by one to understand how actually. Just a minute. My laptop needs to be charged. Sorry for. Right. So basically within the system folder, we can see that there is a blockmesh dict file, and that is the file where we define the geometry and the mesh, and we will generate the mesh now. And it has a control dict file, which has all the control settings for the simulation. And I will show you what is that. Next is their decompose per dict. It actually is used to do parallel processing in this case. Then we have FV schemes, where we define what are the CFD schemes that we are using to discretize the governing equation. Then we have FV solution, where we mention what is the algorithm that we use in this CFD approach to solve the discretized Navier-Stokes equation, right? And there is another blockmesh dict, which is not needed. I'm not going to describe it here. So let us first create the geometry and mesh. And to do that, we basically need to execute the blockmesh, all right? And to do that, the comment is blockmesh. But before that, let us see what is written in the blockmesh dict and how do we define this geometry, right? So that is an important thing. So to do that, let us open blockmesh dict. And we can see that it is quite user-friendly and quite easy. It first sets a scale, which says that whatever number you give, the actual value of the distance given in your geometry and mesh will be times 0.1 meter. Now, if you set up the scale to be 1, whatever number you give will be exactly that amount of meter in the distance. But in this case, you actually multiply the meters by 0.1 with the given numbers. Now, by creating the geometry and the mesh, the first point is that we have to define some vertices, and then we join those vertices by edges and blocks, and then we mesh those blocks, right? So similarly, in this case, we first define these vertices, which is basically the coordinates of the vertices. So the first vertices is 0, 0, 0, 1, 0, 0, 1, 1, 0, 0, 1, 0, etc., etc. And this is in 2D. Of course, you can, if you plot it in a graph, you can see that it's just a square in this case in 2D. And this is the face in the third direction, where the thickness of the cell is 0.1. But in reality, it will be multiplied with the scale 0.1, right? So that's why the scale value is 0.1 here. And every variable in OpenFOAM is in SI unit. Okay, so the distances are in meter. Now, once we have all the 8 vertices, we actually have to define now the edges and the blocks. And we actually, this to define blocks, now because its name is block mesh itself, that means we first create blocks with the vertices, then mesh each of those blocks. All right. And if needed, we define edges, such as if we have an arc in our mesh, we have to define the arc separately, and so on and so forth. But block mesh strict is actually only useful for very simple geometries, such as rectangle, square, circular cylinder, etc., etc. Maximum we can go for a profile of airfoil. But if you want to create a 3D complicated geometry, block mesh is very complicated, and most of the cases it's not possible to use block mesh. That's why we go for snappy hex mesh within OpenFOAM, or we go for some commercial meshing tools and then import those meshes by syntax into OpenFOAM. All right. So now, by creating these blocks, we have different comments. One of these syntax is here hex. That means it will create a hex block with the vertices. And now these numbers, which is, you might be confused, 0, 1, 2, 3, 4, 5, 6, 7 are these vertices. And this starts actually. So let me write down here so that it will be clear to you. So this starts from 0, okay? And in OpenFOAM code, if you give double slash, that means it's a comment. So it is not executed. So that is why I'm writing 0 with the double slash. Now the next one is 1, and so on and so forth. And the last vertices that you define would be 7, right? Then total 8. So now I'm creating a hex block with all these 8 vertices numbered from 0 to 7. And then I'm defining how many divisions they will have. So 20, 21 means X, along X, it will have 20 division, along Y, 20 division, and along Z, only 1 division, because we have given the empty boundary condition in the out of plane direction. So it is a 2-dimensional problem. Now, you can also create grading, and I would suggest you to play with it. It means that whether those divisions will be uniform, or you want to give a gradient, decreasing, increasing gradient, etc., etc. So to start with, I'm giving a simple grading 1, 1, 1. All right. So once we define the blocks, we have to create the boundary patches. And these boundary patches, we have created here 3 different boundary patches: moving wall, fixed wall, and the front and back. And we mention also the type, what type it is. You can see that the walls where we would define the boundary condition, we have already given as wall, whereas the front and back, the front face and the back face, because it's in the outer plane direction, we give the type of empty, because we do not want to solve along the Z direction. It's a 2-dimensional problem. All right. So once that is there, that's my block mesh, and I want to save it. So yes, whatever. And to execute and create the block mesh for this very first tutorial of OpenFOAM, I use the command block mesh. Okay. So the command to create the mesh is block mesh. Now, keep in mind, if in your terminal, you have not sourced the BASRC, or if you have not activated the OpenFOAM by the keyword OpenFOAM 2306, something like that, this command will not work, of course, because your terminal doesn't know that you are using OpenFOAM, right? So now I have already done it, hopefully. So it should work, but it doesn't work. So it gives some error, which is interesting. I understand. So that's also an interesting error. So to learn OpenFOAM, I would suggest getting errors is useful. They are friendly. Once you see the error, you use your common sense, read the error, you will be able to understand where you are doing mistakes, right? Now, I know you are muted, but I'm tempted to ask you, what do you think the error here is? Now, in the interest of time, I will tell you the error here is because I am in the system folder, right? So within the system folder, it cannot find the actual place to execute the comment. That's why it gave the error. So basically I have to do cd ... and then I use the same comment. It should work, and it worked. Okay. So it shows you that all the execution commands have been done. And then the next step, when after you created the mesh, is to check whether the mesh is appropriate, the non-orthogonality, the skewness of your cells are all right within the limit or not. To do that, the command is check mesh. Sorry for this pinging sound because I'm confusing between two different computers. So to check the computational domain and the mesh and the quality of it, you give the command check mesh, and it shows you all the statistics about your mesh. All right. So let's try to understand what it shows. So it shows that it is creating for t equal to 0. You have this number of points, you have this number of faces, you have this number of internal faces, etc., etc. Here it shows that it is checking the topology, boundary definition is okay, cell to face addressing okay, everything is okay, number of region is okay because we have not defined multiple regions, and every patch, how many cells, etc., etc. No phase zone, no cell zone is defined. Of course, we have not defined anything. No point zone is defined. And then it is checking the geometry and tells you all the statistics about the quality of the mesh. And ultimately, it also tells you whether the mesh is suitable for doing this kind of computation or not. All right. Now that we know that, we go back to our constant folder. And if we see what is there, interestingly, now this polymesh folder has been created because you have now generated the mesh, right? Which is actually in the polymesh folder. And if we go to the polymesh folder, you can actually see that there are all these informations have been created. What is my boundary, faces, neighbor, owner, points, etc., etc. All right. Now that my pre-processing is done, I will go towards solution. And to do the solution, I need to first set up the solver, that which solver I need to use, what are my CFD schemes, what are my linear algebra solvers, what is my tolerance, what is my level of accuracy I want, etc., etc., right? So, right. So basically, I am now in the polymesh folder. So I will go back one step, two step, and I should go to system. And here now we will look into the control dict file. All right. So in the control dict file, it's one of the most important file, and you can see that here we need to mention the solver that we need to use. Okay. And the solver that we are using now is OpenFOAM. Okay. And as I mentioned that OpenFOAM is the basic incompressible Navier-Stokes solver. Then we give the simulation setup as start from start time. And what is my start time? I can give as 0. Now, what's the use of this? The use of this is that if you have run one simulation already up to certain end time, and you want to restart it for the interest of, like for extending the simulation for more time, you can, instead of start from start time, you can instead start from latest time. Okay. So I can actually, I'm writing here so that you can make a note. I can start from latest time. Okay. And what that will do is that will override the value of the start time and take the latest, what is your last time of simulation, will start from there. So this is useful for restarting the case. Now, if we also, it tells the stop at end time, and end time is 0.5 second. Now, delta t is this, which you need to choose as per your problem. Now, this is important. What is write control and what is write interval? Now, your simulation happens every runtime, right? So every delta t, what is your delta t value, which is here is 0.005. However, because computational fluid dynamics simulations are computationally very intensive, you basically want to refrain yourself from saving all the data. So you need to choose at what, after how many time step, you actually need to save all the field data to visualize it. All right. Now that is my right interval, and right interval 20 with the right control of time step means that every 20 time step, I am saving my data. Okay. And I'm writing in ASCII format and etc. etc. These are normal general setup of how you want to write your data. Now, once we understand this, we go to now my another file, which is my says what is my algorithm, right? So that is stored in FV solution. And if we go to FV solution, sorry, it is a file, so I cannot do CD. I have to open the file. So let's see, what are the files? Yeah. Right. So if I see my FV solution, I would see that this P and U is my field variable, as I have already explained. Now, coming down, you have the algorithm by which you are solving the discretized Navier-Stokes equation, and which is PISO. The full form of it is pressure implicit splitting of operator. It's a CFD scheme by which you, in the finite volume, it's one of the finite volume schemes by which you solve the discretized equations, and it has multiple correction loops and leading to finally solving the pressure Poisson equation. And I'm not going into the details of the scheme because that's another topic of discussion. But using the PISO algorithm, we can select how many correction loops we can have. If your maze has a significant non-orthogonality, if we want to include any correction to increase the accuracy, in this case, it is 0. And if we have any pre-reference value, which is 0 in this case. Now, the important thing is for P and U, these two pressure and velocity equations, ultimately, in terms of solving this discretized Navier-Stokes equation, it leads to the solution of some linear equations. Linear equations we need to solve in terms of their matrix form, right? So, and to solve linear matrix equations, we need some linear algebra solvers. Like, for example, you have learned in your course LU decomposition and etc. etc. Those are like some of the linear algebra solvers that we use to solve the matrix equations. In this case, we have more complicated linear solvers that is coded within OpenFOAM, which we will use. So for pressure, we use something called PCG. Okay. So this is CG is conjugate gradient method, and P stands for preconditioned. So we use a preconditioner to improve the stability of this method. So it is preconditioned conjugate gradient method. And with the preconditioner is diagonally incomplete Cholesky. Okay. DIC. So, and then I give a tolerance for my P calculation and the relative tolerance. And ultimately, once the tolerance is satisfied, we actually have two steps in this PISO schemes where the pressure correction loops works. And finally, by solving the pressure Poisson equation, we come to another final form of pressure, the corrected pressure, which is P final. And for that also, we can use the same tolerance values. And for velocity, as the solver, we use something called smooth solver. And all these details of these codes, what is actually PCG, what is actually smooth solver, every source code is available to you within that folder that I showed, within the folder SRC. Okay. So you can go back and look into the code, how they are coded. And then with a smoother symmetric Gauss-Seidel solver with the tolerances we use. So I hope now it is clear in the beginning level. And the only thing now we need to mention is what kind of CFD schemes that we need to use to discretize the equation, right? So here comes the solution part, but before solving the equation, we need to discretize it, the divergence term and etc., etc. To do that, we actually open the FV scheme file. And we see here, what are my schemes? So my DDT schemes is Euler, okay, which, it's a first order scheme. We have gradient schemes is Gauss linear. We have divergence schemes as Gauss linear. We have Laplacian scheme as Gauss linear orthogonal. Interpolation scheme is linear. SN grad scheme is orthogonal, etc., etc. So the point here is to show you that all these things can be changed. There is no default thing. And all these values or all these schemes need to be changed depending on what problem you are going to solve, right? How steep your equations are, etc., etc. So that is the benefit of using OpenFOAM, is that you know everything, all the settings that you want to use, and you can change it. You can give another method instead of that. I hope that is clear. So now that we know what are my files, let us run the solution mode. After that, we will go to the post-processing mode to see it before we go to some more discussion about the source code. So to run the simulation, because my maze file is already generated, we actually will call the solver. That is the keyword for running the simulation in this case. And that is, I have already mentioned, is OpenFOAM. Okay. And if we run it, it again shows me error because I did the same mistake. Sorry. So I have to go back and I have to call the solver, and it runs. And while running the simulation, it shows you at every time step, okay, at every time step, because we have given the delta t as 0.005, at every time step, it shows you the statistics of the CFD simulation as what is my current number. If you know what is a current number, it's called the CFL number, which actually is depending on the stability condition of your algorithm that you use. And it shows for that time step, how many iterations it needed to converge to satisfy the tolerance. It showed basically what is my residuals, and you can also plot these residuals over time to see that your final residuals are always below a certain threshold value, so that you can actually get to know that whether your simulation is accurate or not, and the results can be believed or not. All right. Now, once we run this, we actually want to visualize it, right? So basically, if you go back to your main case file, and you can see that some folders are generated, and we will get to see what are they. So now you see that apart from your 0, constant, and system folder, we have 0.1, 0.2, 0.3, 0.4, and 0.55, which corresponds to the right interval. If you can remember that in control dict file, we have set up the right interval to be, I think 20 times, or I've forgotten. You can go and check in this tutorial, and it actually shows you where you are saving these files as per your right interval, right? And if you go to each of these time directory, all right, so if you go to 0.1 for say, and you can see that it has the solution files. That means by solving the discretized Navier-Stokes equation, you get the fields that you want to get, right? One is your P, the pressure values in all the coordinates at that time step, the velocity values U, and the phi is the flux of the volume, and so on. Right. Now, the solution step is over. Next, what we want to do is basically we want to actually visualize it or do some sort of post-processing. And as I showed you previously, that we will use ParaView. for this case, because that's an open source option to do the post-processing results. And I have already installed ParaView in my computer, and you also need to install ParaView separately, or it can also come with the OpenFOAM package itself. And the comment is ParaFOAM, but it may actually be an older version because maybe in your OpenFOAM setup file, it is linked to a much older version of ParaView. So I would suggest you to install the latest version of ParaView, which is available from the ParaView website, etc., etc. And to do that, we have to go back to the system folder. Sorry, not system folder, the case folder. And let's see where I am. Yes, I'm in the case folder. And here we have to create a file with an extension .foam, okay, which would be read by ParaView. And to create that file in Linux, we use basically the command touch. And I will just give results.foam. So this .foam, this extension is very important because this is the extension that ParaView can read, apart from the other extension, which is .vtk. Okay, so the VTK, I mean, to make it a VTK file, you have to actually convert the OpenFOAM files into VTK files, which is possible, but it's an advanced stage of analysis. But for example, if you create this results.foam, and you can see that in your folder, you will have a file called results.foam, which can be read by ParaView very easily. And to call the ParaView, I call ParaView and results.foam, and it should actually open my ParaView window, and which you cannot see. Let me try to reshare my ParaView window. Okay, so stop sharing. Share screen. Yes. Right. So now you can see my ParaView window, which is just opened by calling that results.foam file. All right. And now to load the data into the ParaView folder, we have to first apply, of course. And by doing application, we see the results. Now, I will show you some basic uses of ParaView also, so that you can get started with the post-processing of your first simulation, hopefully. Now, first of all, you notice the fact that it shows you the time value of 0.01. Okay, so that is the default case for ParaView. And if you want to start from the zero time, you actually, hopefully you can see my cursor, and you can see that skip 0 time is actually ticked. So to untick that, we untick it and apply, and we go back to 0. Now at the 0, you can see from the color bar that everything is 0, 0 values, which we have set as the initial condition. And then if we go one step, of course, here we choose the variable, state variable that we want to visualize. And we have here mainly two, right? And it shows the cell value or the grid value, etc. And if I choose the velocity, if I go to 0, clearly it explains you the initial condition that you give the 0 value everywhere apart from the cell value, right? And apart from the cell values at the top wall, which is the lead. And now if you go to the next step, as the lead moves, the velocity profile changes within the flow field, and you can visualize it. And similarly, you can visualize the change of pressure. So the pressure was 0 everywhere, and then the pressure gradient is created within this flow field. Okay, so this is just to visualize. It has many options, which I will try to show you a couple of them to know what you can do with ParaView. It's a very powerful software, right? So first of all, if I go back to velocity, and you can see that at 0.1 time second itself, it is like this. And then if you go to the last last 0.5 second, there is no change. So the almost the flow field has been settled to almost kind of steady values, right? So what we can do with it, we can first see these are the some of the options. So if we choose first the the variable to be velocity, we can observe the magnitude or its different components. So because this problem is 2D, Z component doesn't make any sense. So we have X and Y component and the magnitude, and we have different ways of visualizing it. So you are currently seeing as a surface contour plot. If we do as surface with edges, you can also see the grids. All right. And then there are many other options. One of them is surface LIC, okay, which shows you the line integral convolutions. LIC means, which basically shows you path lines, more or less. Okay. So you can see that there is a rotation created within the fluid volume by actually moving the lead, and which is clearly computed by integrating the velocity component. So this is again a derived quantity from the velocity, and we can visualize the streamlines. All right. Now, if you want to observe vorticity, okay, I hope that you all know vorticity. Then what do we do, right? So for that, we need to first calculate vorticity. Now, I will show this example as an example on how you can use function objects in OpenFOAM. All right. Now, what is function object? Now, function object is some code, some auxiliary codes which helps you to analyze, which helps you to calculate some derived quantities from your basic state variables like velocity and pressure by using the post-processing functionality within OpenFOAM. All right. Now, it is clear that you have the solution of these discretized Navier-Stokes equation as the pressure field and the velocity field. And now, from the velocity field, we will calculate another derived quantity, what is called vorticity, which is nothing but the curl of velocity, right? And the measure of vorticity is circulation, if you know the basic fluid dynamics. So let's try to share my terminal again, and where we are, I think. Yeah, hopefully this one. Yeah. So here, to calculate vorticity, we have to use the post-process functionality. And the comment is post. It's very easy to remember because that's how it is written. So oops, nothing is working. What is, oh, sorry. So ParaView is open here. So I have to first close the ParaView. Okay. So I just press Control-C to close the ParaView to get the control of my terminal back, right? Now I see that I have these data. Now I use the post-process functionality, which is called post-process, then hyphen function FUNC, and we have to give the name of the function object that we want to use. And OpenFOAM already has by default a function object to calculate vorticity. So we write vorticity. Okay. And hopefully that works. Yes. So it calculated the vorticity from the volume vector field velocity at every right interval. So now you have to keep in mind that this post-processing or function using the first function object can be two types, either online while the simulations are running, or after the simulation has been run and you have the solution. Now, if you want to use this function object as a post-processing tool after the simulation is done, you will only get the data where your right interval is defined, because in between the data is not saved, right? But if you want to include this function object within your simulation and run it for every time step, such as for a wing, if we do a simulation, we want to measure the aerodynamic loads and moments. We can calculate the lift, drag, and moment by the function object called forces, which we can include in the simulation to calculate in every time step. And that has to be done in the control dict. But here I'm doing the post-processing once the simulation is run already. So it only does it for the data that you have saved, right? So this is like 0.1, 0.2, 0.3, 2.5. Now let us call the paraview again. Okay. And let me share the paraview screen with you again. Stop share, start sharing screen and paraview. Okay. Now, if I do skip 0 and apply, you will see that in the variable list, apart from velocity and pressure, we have another parameter, which we have, or another variable that we have now calculated. It's called vorticity, right? Now, you have to keep in mind that vorticity, magnitude of vorticity is not that important, rather than vorticity about which axis we want to see, right? Here, the vorticity or the rotation of the flow is about the Z axis. So we have to select which component we want to see, that is vorticity Z. And then you can see surface, you can see many other types, but surface makes the most of the sense here. And this gives the vorticity Z, all right? Now, suppose that you want to change the color bar or the range of it. So now the range of it gives you some values, I don't know, some arbitrary values, right? So if you want to change it, you can change it here. Okay. So this option gives you the setting the range. Okay. Now let's say I want to give -10 to 10. I want to see in this range, right? And I want to rescale it. I see something like this. Now the results is right or wrong, I don't know, because it's just I'm seeing it in a coarse mesh, and this is just to show you how to calculate it. But when you have a proper problem set up with proper conditions, the vorticity will show you proper physics that you are expecting, which we will see now in a moment for another example where we will do flow past a cylinder.
And then,
yes.
Hello. Yeah, if you want to take a break for 5 minutes, we can continue.
Yeah, that's what was my plan, that we have now crossed 2 hours, and I will take 5 minutes break and we'll come back and start